Yeah, way to fix it. Yeah, but you see the sound on another point is this sound.
And you have idea what only this book?
One book, yeah.
From Tika. Tika.
No, Symptom is this.
Okay, as I said, so last lecture in private, I decided not to discuss superfluidity just because not everybody was here, and this time I showed you some slides on current development of cold gases. Of course, I will ask Patricia to make a printout and to give it to everybody. You will all get it as printed, or you can download it as PDF files. If you like, I put it on the web. But today we come back to discussion of superfluidity. This will be the last lecture devoted to Bose condensation, and tomorrow we continue with magnetisms. And those who missed this part about semi-classical magnetism, don't worry much, because everything will be repeated in great details when we discuss a quantum version of the same thing. But before I proceed with the superfluidity, I would like to answer questions written to me in emails regarding exam. Again, sorry if those who expect that I respond to emails immediately. I apologize that sometimes it takes me days to respond, and I prefer to minimize my writing email, so it's better if I answer you just verbally. But again, if you need really something urgent response, don't worry. If I am not responding in one day, nothing happened. But in 2-3 days, I'm responding to all important or less important questions. So, exam. The exam will be written, and written exam will consist of 3 questions. 2 questions will be just formulated as questions which we discussed, for example, superfluidity, Landau criterion, or diamagnetism. So what you will need is to write down detailed answer on this question, and the third question will be problem. Summarizing, written exam, 3 questions, the last question is a problem. All questions will be valued in points, and I will present you the rules, which points corresponds to which grade. I mean, generally I do it 100 points, and depending, say, on receiving homework, for example, usually I use that to have A, it's necessary to have 75 or 80 points and more. So then between 80, say, and 60, there will be B, and 50, 60 will be C, and what is less than 50 will be failed. But don't be afraid. I think, first of all, I will let you use any kind of your lecture notes. It will, or any kind of book as you like, because, as I'm always saying, the exam is for you, not for me. Therefore, if you just copy everything, well, the question will be formulated in such a way that it will not be enough to copy everything from the lectures on a book. So you will need to think a little bit. But I believe, would you just be able to reproduce what we did in the lectures and what you solved in your homework, it will be sufficient to pass exam. So don't be afraid. I'm not going to make you fail, and this is not my goal. So those who understand things will never fail. But of course, to get A, it will be enough difficult, and it will include solution of the problem. And to get excellent, I didn't yet make my mind regarding this, but usually excellent means you have more than 90 or 95 points out of 100. Okay, this is how exam is going to be organized. As far as tutorials are concerned, I did not yet make plans. Namely, my assistant will be available at the end of March, and she is traveling too. So we will optimize this problem hopefully next week. Since you asked me to change the date of lecture on 24th, it is done. So you will not have my lecture on 24th. I spoke with Patricia. Instead, you will have lecture on Friday on 26th. I think it's at 11 o'clock. This is at least what we planned. So take your time, prepare for exam, and don't split from other things. Regarding the last part of the lectures, namely I asked you a question and only one person responded. Actually, what would you prefer, to have a little introduction to Green's function, or to have more lectures about transport, quantum transport, including resolved systems, for example, in effective equalization? Still, I'm undecided yet. I already planned tutorials which will anyway refresh the knowledge of Green functions for ordinary differential equation, having in mind this Green function appearing first from the Schrödinger equation in the scattering theory, and second, then you will get a Green function which depends on the energy and momentum, or in the second tutorial, the Green function which appears in so-called block equation describing behavior of spin subject to time-dependent magnetic field. We will discuss this problem a little bit in the theory of magnetism, but in the tutorial you will learn how to solve this problem, namely linearized version of it, with the help of the Green function of ordinary linear differential equation. So you will see two ways to get a Green function from either Schrödinger equation or equation of motion for magnetization. However, in both cases, it's kind of single particle Green function. In one case, it was indeed a matter of linear differential equation. Since we know that quantum mechanics is linear theory, we have a superposition principle, and there is no way to have nonlinearity except you treat your interaction as a part of nonlinear theory, which then leads to nonlinear Schrödinger equation, but still the superposition principle holds. However, the behavior of spin or magnetization and equation of motion is intrinsically nonlinear. So linearizing it will mean using some approximation. So then, of course, as I said, these two examples represent single particle theory. And Green functions which I wanted and I had in mind to discuss with you is, of course, Green function of many-body theory, the building block of many-body theory, which allows you to construct consistently perturbation theory, starting from single particle Green functions, and then identifying class of processes, class of physical processes. One can make a partial summation of processes, and perturbation theory sometimes becomes more pronounced in advance because it allows sometimes to sum up special classes, as I said, of diagrams corresponding to processes, which mean going beyond the second order perturbation theory. Okay, and in some cases it allows also to find some asymptotically exact solutions of the theory. So, as I said, you will at least get part of it in two tutorials, but as far as final decision regarding this many-body Green functions, I cannot yet say anything. Whether I follow this way, which I would say requires some time, and it's not so easy to do it in a short period, or we better discuss not methodological part but physical part and go broadly in the direction of disordered system, as I said, weak and strong localization and transport in disordered systems. Okay, today we discuss superfluidity. Let's start with experimental facts, which actually were driving force for theory of superfluidity. Anyway, do you have any questions regarding interacting Bose-gas, weakly interacting Bose-gas?
Can you tell us more about the effect of boundary condition of Bose system?
As I said previously, typical experiment for cold gases is designed in such a way that first of all one traps certain amount of atoms in magneto-optical trap using several ways to cool system down. It's quite tricky actually, and many things like Pomeranchuk effect, like Sisypheus cooling are used. I'm just mentioning, I don't have time to discuss with you experimental techniques to prepare system in magneto-optical trap and cool it down for sufficiently low temperatures, because starting temperature should be low enough in order to see the effect. But the trap itself is a kind of confinement potential. For example, parabolic potential, if we are talking about one-dimensional system, suppose that this is a coordinate and this is ux, and then a particle will condense not at the state corresponding to k equal to 0, but at lowest energy state of potential. In principle, it's still single particle Schrödinger equation in order to find the wave function. It's not quantization in a box where the wave functions of particles are just plain waves. However, one can solve this Schrödinger equation, find the secondary quantized state, and investigate questions what happens with a condensate if you have condensation not in a box but in some specially designed potential. And what I said to you, and you can read more about it in the book. I give you today two references on the book, one about superfluidity, excellent book, and another one about Bose gases, is that condition for not condition, I mean the calculation of number of particles sitting in a condensate actually is very much different, not methodologically, but from the point of view of answer, whether you have a box where your wave functions are plane wave, or you have some confinement potential. The best way to do it is to introduce a density of states, the quantity which we widely use when we were discussing the Fermi systems, and the answer which I present you is that for parabolic trap, number of particles in three-dimensional trap in a condensate is 1 minus over T0 to the power 3, compared to power 3 half. So this is trap, the answer should be contrasted to the answer for the box, which is 1 minus t over t0 to the power 3/2. Introducing this density of states and considering low-dimensional systems, you can equally calculate fluctuations and see how number of out-of-condensate particles, the quantity which we calculated last week, depends on the temperature and the size of system, and you see that the statement which I made, namely that there is no long-range order in a system characterized by short-range interaction in system of two-dimensional geometry, except for the temperature equal to 0, or in any case in one dimension. This statement is modified for the trap, and the reason is that, of course, trap modifies your density of state, and you have some confining potential which can stabilize condensation even in low-dimensional systems. What then people do, say in experiment, as I said, they constructed such kind of system. They lowered down temperature to make it sufficiently low, such a way that all particles, all bosons are sitting on the lowest energy level of the potential, and then they remove the potential at all. So if at some moment the trap is just switched off, then you see how your particle starts to escape, and measuring in this time of flight experiment momentum distribution of the particles, you then see the fraction of particles occupying the lowest level of the potential. Namely, if you are at temperatures larger than T naught, then you see that your distribution is broad. However, if you are below T naught, temperature of condensation, then your distribution is very much peaked, like we discussed. So the distribution of your particles should consist of nearly delta function, and which describes particles in a condensate. So this is average number of particles at P as a function of P, and then there should be some tail or wing. So measuring the structure of this peak, one can make a conclusion whether we are in situation below or above critical temperature. So now the reference. The reference on the book about ultra-cold gases. This is a very good book. It's a Smith, and I don't remember initials. For basic, it's Chris Basic. I think it's like this, and it's called something like ultra-cold gases. It's a very nice book, published something like 10 years ago. You will find it in a library, and it's very detailed, very good, very well written, and contains a lot of interesting information and very up to date. So this is about both condensation, including trap, including new techniques to adjust resonances. I mean, how people work with these ultra-cold gases, how they adjust the scattering length through so-called Feshbach resonances. The book about superfluidity is famous book of Feynman, Richard Feynman, and it's called Statistical Mechanics. It has several editions. You will find it in the library. It's a very good book because it is written, first of all, by excellent physicists. It contains a lot of physics inside, experiments, interpretations, motivation. So Richard Feynman was a great physicist. He's Nobel Prize winner. Getting his Nobel Prize also for introduction of this method of Feynman diagrams to calculate many body effects in high energy physics in many body systems. But the book is really excellent. Those who are interested in this topic, please read. Now I'll come back to superfluidity. Okay. So what were the experiments actually? The story started in something 1930s. The word superfluidity appeared in 1937, where Kapitsa wrote his paper in Nature. Paper is fantastic, 1 page, and he got his Nobel Prize actually for discovery of this effect something like 40 years later. The story started with a measurement of specific heat of liquid helium as a function of temperature. It appeared that, so this is helium-4. It appeared that below some temperature, which is 2.18, the behavior of specific heat changed dramatically. Namely, it was kind of T-cube on the left-hand side, and it had kind of log T minus T node on the right-hand side, and this is T node. And therefore, since this behavior resembles graphically Greek letter lambda, this behavior of a specific heat for helium was known as lambda point. So behavior of system, as I said, is dramatically different to the right-hand side, which is sometimes referred as a helium-1, and to the left-hand side, which is helium-2. So the question is, what happens at this point, 2.18 Kelvin? What is a characteristic property of the phase to the left from the critical point? And it appears that the phase 2, namely below critical point, cannot be seen. It's not a liquid which can be boiled. In a sense that this liquid has infinite thermoconductivity. And this is surprising. Then people start to think how to explain it, and they arrived at something which end up in a two-fluid theory. But before coming to two-fluid theory, I would like to mention other experimental stuff. First of all, another experiment showed, and actually Kapitsa experiment, this specific heat is not, showed that this liquid, namely helium in a phase 2, runs through the very narrow channels, capillaries, without any friction. Namely, if you put helium to tube, some kind of pipe in a helium to liquid, then liquid starts to flow through the capillary and actually fontaines out of it. And this fontaine effect is also known and puzzling that time. So how it happens that you have something cold and something hotter there, and cold liquid goes up and fontaines. Then there was experiment with 2 reservoirs. Like this. One is at temperature T1 plus delta T, and another one is at T1. And again, the flow was detected as coming from the cold reservoir to the hot one in order to make hot reservoir cold, which again was surprising. Usually we have other way around. If we have hot and cold, then hot substance goes to the cold reservoir in order to make cold stuff hot. Here it was other way around. This was a puzzling stuff. And then there were experiments by Eleftherios Donikashvili, great Georgian experimentalist, who did experiment with disks. Suppose one has helium in the phase 2, and one put a bunch of disks inside of this helium. And then one makes little torsion, little rotation of this disks, and it allows to measure inertial momentums. For example, in this system, and it appears that this inertial momentums change such a way as part of the liquid being responsible for friction, the same way as here, start to decrease in the system. Namely, it looks like, and it was quite natural explanation, that below this temperature T node, the liquid helium behaves like two liquids. One of them is superfluid, those who comes through the capillary without friction and responsible for infinite thermal effect. So this one is known as thermomechanic effect. So there is, so to say, superfluid component which disappears at temperature equal to 0, and there is a normal component which, so this is a raw density of two liquids, this is the temperature, and this is, so to say, normal component, and this is superfluid component. So what we have is a total density consists of superfluid plus normal, and at sufficiently low temperatures, whole substance behaves as a superfluid, and at temperatures higher than T0, the liquid is completely normal. So there is a phase transition, and the superfluid density may be identified as an odd parameter. Yeah. Moreover, in the experiment like that,
I do not understand this experiment.
one has helium-2, this substance, where superfluid component already exists. So then one make a reservoir filled with helium-2. Then one put a bunch of disks, stock of disks, and start to make torsions this way and that way. As one can see, the superfluid component is not responsible for any friction into the system. It's superfluid. Therefore, one can measure with these torsion oscillations the fraction of normal component, the density of normal component. And this is what has been done. So would one not have a superfluidity, then of course the density of normal component will remain a constant. But the way to see the decrease of normal density when you lower down temperature was an identification that something happened in total. So the fraction of normal component becomes smaller and smaller, then there should be transfer of normal component to some another state, which was eventually called as a superfluid. This experiment actually is really crucial because, say, in 2004, people start to investigate possibility to have superfluidity in the system with not broken translation invariance. You see, here we discuss the liquid. There is no translation invariance at all. There is no crystalline order, so the superfluid substance is discussed in liquid. However, in 2004, two experimentalists in Penn State, namely Moses Chan and Kim, argued that what they observe is a kind of superfluid motion in the system with a periodic, with a crystal structure, so to say, with translation invariance. And this substance, which again is a new state of matter, was called supersolid. I'm not going to discuss because it's superfluid but solid at the same time. As I said, it's coherent motion of a system with a translation invariancy, and the way they did it was precisely the same. They repeated the Andronikashvili experiment in helium under very high pressure of the order of hundreds of bars, and what they measured is inertial momentum. As you see, measuring inertial momentum is the same as measuring normal density. So if you deviate from the 100% of component, so if your inertial momentum shows some deviation, then it means something happens with the system. And they detected it and argued that this is nothing but supersolidity, which was discussed theoretically in early 70s. So you see that the story about superfluidity now transfers to experimental observation of supersolidity, which is one of the interesting open questions of nowadays physics. It's still not accepted widely whether it's in fact a new state of matter or there is another possibility to explain this observation, namely that the inertial momentum are not classical, so to say. They deviate from the 100% normal component. Other possible explanation would be superfluidity along grain boundaries. So the helium forms under such high pressure forms liquid crystals, and these liquid crystals have kind of multi-domain structure. It consists of grains, and then the capillaries, which exist here, may provide the room for superfluid flows, or it's some coherent motion of domain wall. So there are many theories in the market which either support supersolid state or disprove supersolid state. But this is one of the interesting questions of nowadays condensed matter physics. But Andronikashvili experiment becomes so important and was so important that actually the same idea applied to the solid structure was able to provide first reliable information about this non-classical inertial moment. Okay, so this was experiment, and as I said, there was a two-fluid theory suggested by Landau, which actually postulated existence of two density, superfluid and normal, and then, as I said, the phase transition occurs. Also, in order to describe the thermodynamics of this system, Landau postulated the excitation spectrum of the system, which should have the form, so this is epsilon p as a function of p, It should be non-monotonous function of p. At small p, it demonstrates linear behavior, and this is what we would call phonons. And there is also minimum at some p equal to p naught, which then was called Roton minimum. We discussed the origin of this roton, why it is rotation, and what kind of rotation appears in this system. So as I said, Landau, in order to explain this experiment and in order to come out with this two-fluid theory of superfluidity, postulated the spectrum of that sort, phenomenologically. Moreover, very simple arguments allowed him understanding superfluidity criterion, which is then called Landau criterion. One doesn't need to make a lot of calculations. It's very physically transparent. Let's repeat these physical arguments and to understand their meaning. The criterion says us how quick the superfluid substance should move through the pipe, through the capillary, in order to remain superfluid. Quite understandably, so if one pushes this superfluid substance very quickly with a high velocity, then there is a friction on the walls, and therefore superfluidity should be destroyed. So how this friction occurs in the system? So friction occurs, let's assume that we have kind of pipe, and there is a liquid, and let's for the moment use a coordinate frame associated with the flow. So in this frame, liquid doesn't move. So we have chosen this frame. Therefore, all excitations are associated with emission and absorption of phonons to the walls of the capillary. Okay? So now, let's come to the laboratory system. So in the moving frame, we wrote that we have momentum, which is related to the wave vector through simple formula, and we have energy of excitations, EP, equal to EQ. We don't specify this character of dispersion. But as I said, in the system where liquid is not moving in the state of rest, any kind of friction is associated with the excitations which then emitted and absorbed by the walls. Step number 2. Let's go to laboratory frame. And write down the energy in the laboratory frame. So E in lab frame is equal to E prime. We know it from classical mechanics or classical fluid theory, plus P prime times W plus the energy of liquid mW square half. So you see, there is a kinetic energy of the liquid which is anyway positive. in order to have system be superfluid, at least this part should be negative in order to compensate the positive kinetic energy of the liquid. So in order to have superfluidity, one needs to have E prime plus P prime V to be smaller than 0. But this is E prime is nothing but EP. And moreover, we see that P and W are antiparallel. So the scalar product, when I come from moving frame to the coordinate frame, P times W is equal to minus E W. So P prime is equal to P. Okay, from this criterion, we should say that in order this to be negative, we need to have V bigger than epsilon P over P. Negative means in order to create a friction. So this part is negative when we have a friction and when energy of our liquid dissipates to the walls. So this is a critical velocity. So if V is bigger than critical velocity, there is a friction. If W is somehow smaller, VC, then no friction, and liquid runs as a superfluid. So existence of this critical velocity was predicted by Landau, and depending on whether such kind of critical velocity exists or not, we can either have or not have superfluid. Let's discuss it considering some special forms of the excitation spectrum. Namely, we discussed different examples, sound-like, quadratic, gapped. So let's repeat this discussion and see when the superfluidity is possible and when it is not. So first simple example, number 1. EP is equal to P squared over 2M. When we just have non-interacting particles, the question which we address, whether non-interacting particles, bosons, can possess superfluid motion, defined by this criterion, and this is nothing but Landau criterion or not. So we have P squared, epsilon P is a function of P. Let's find the critical velocity. Vc is epsilon P divided by P in the limit P goes to 0. Because this is the question whether this superfluid can be achieved, and if we divide, we will have P over 2M is equal to 0. So the answer is that for non-interacting particles characterized by quadratic dispersion law, the superfluid velocity, critical superfluid velocity, is equal to 0. So as long as you start to push the liquid with this dispersion through the capillary, friction appears for any arbitrary small P or W in the system, which means that system will exchange excitations with the capillary, and this will create a friction. Example number 2. If epsilon p is equal to Cp, so we have our beloved phonons in the system. So then, if we do the same, we calculate critical velocity, which is Cp divided by p goes to 0, then the critical velocity is nothing but sound velocity, which is, and this is a constant. Namely, for the system characterized by linear dispersion law, if v is larger than the phonon velocity, we have a friction in the system. If somehow the fluid runs with a velocity smaller than the sound velocity, it remains a superfluid. In superconductivity, we will discuss phenomena associated with destruction of superconducting state when you run a current through the superconductor. And this is precisely the phenomenon of that sort. If you take a superconducting wire and apply large voltage such a way that there is a high current running through the system, current being larger than some critical value will destroy superconductivity. Well, let's take the last example. If we have this phenomenological Landau spectrum, which consists of phonon part and roton part, then the critical velocity is defined by tangential. So you see, if the system runs with a velocity smaller than defined by tangential, then there is no way to excite these rotons. So here, epsilon p is equal to Cp for p smaller than something, and delta plus p minus p naught square over 2m. So there is a critical velocity in this case 2, and system can be superfluid. This was one of the reasons for Landau to introduce phenomenologically this kind of spectrum. It should possess phonon branch at very small momenta, but still have roton minimum associated with creation of vortices, which we are going to discuss right away. Okay, what can we learn from here? What can we learn comparing these two examples? Very important message is that the ideal Bose gas, the Bose gas which doesn't contain any flavor of interaction, cannot be superfluid. Why? Because if we have free motion with the energy p square over 2m, the critical velocity, in according to Landau criteria, is equal to 0. However, if we recall our calculations for weakly interacting Bose gas, then epsilon p was equal to square root of 2 times epsilon p u naught over v u naught over v times n plus epsilon p square, which then for small p was square root over u naught n over m times p. So you see, the sound velocity appeared in the system for small momenta, and the sound velocity is proportional to the square root of the interaction, and the density of the condensate. So the condensate itself, although we have Bose condensation phenomena in non-interacting Bose gas, which is solar phase transition, does not lead to any superfluidity. For superfluidity, one needs to have interaction between particles, which then softens the dispersion relation, leading to acoustic-like behavior of spectrum at very large wavelengths. So the message which you have to learn is that Bose condensation itself doesn't assume any superfluidity. And what is responsible for superfluidity is interaction. Okay, is it clear? Because now I come to explanation why this Roton minima should exist in the system. So you see, today we don't do any lengthy calculations at all. We just make estimations and draw some conclusions out of this simple physical estimation. But it doesn't make physics behind of this phenomena very simple. Okay. What did we discuss previously is that condensation can be understood as increasing of the de Broglie wavelength. So this is the Broglie wavelength, and lambda is h bar over p t, which is h bar over 2m temperature. When you load down the temperature, then the de Broglie wavelength becomes larger, larger, and larger, and at the end of the day, namely at sufficiently low temperatures, you have the de Broglie wavelength so big that your condensate is described by unique wave function. But before coming to condensate, and the criterion to come to the Bose condensation is when the de Broglie wavelength becomes of the order of the interatomic distance in the gas. So when this happens, we have Bose-Einstein condensation in the system. And as I said, when we put temperature even lower than that, then your condensate appears as giant matter wave in the system. So it's main body coherent phenomena such a way that your main body state can be characterized by unique coherent wave function. When we say the wave function, let's write it down. So your psi, as we know, the wave function consists of the modulus, and modulus is n node of r over v. So the wave function depends on r, and then there is a phase I, chi, r. So the wave function has a modulus and phase, and the modulus of the wave function is in proportional to square root of total number of particles sitting in the condensate. And the wave function of that sort is normalized such a way that the integral or wave function over all coordinates is equal to number of particles in the system. This is a many body, not single particle wave function, which is characterized by modulus and global phase. Well, we can say that at sufficiently small temperatures, we know that modulus depends on temperature very slightly, and actually for uniform state, namely if we are sitting in the box, then the density is uniform in the box. If we are in a trap, and there is a good exercise to calculate how the density of particles depends on the distance from the center of the trap, then at small deviations from the center of trap, suppose we have a parabolic trap, it's also almost constant. So therefore, we may replace this factor by some constant and concentrate on the phase of the wave function and see how the superfluidity manifests itself through the behavior of the phase. In order to do it, and we are in quantum mechanical treatment, which resembles very much single particle quantum mechanics, because the wave functions look like that, still don't forget that this is made by a wave function. Let's define the current. Current is h over 2m. Here it's psi gradient psi bar minus psi bar gradient psi. So if we plug in this wave function, which we have just discussed, and ignore the coordinate dependence of the modulus of the wave function, and the reason to do it is because this dependence is very weak, and the gradients of the number of particles are negligibly small in the box everywhere, or in the trap everywhere except the boundary of the trap. Then plug it in here, we get that this is Hn density over m, and here it's the gradient of current. So the current in the system is proportional to the phase gradient. Okay, if we write it as density times velocity, then we can write down that velocity is equal to h over m gradient. So we have a liquid and we have a potential motion. Potential motion means our field of velocities satisfies the equation number v is equal to 0. And since v is itself gradient chi, we have nabla times nabla chi is equal to 0. So let's take some region. First, single connected region. Then the integral over gradient times v ds according to Stokes' theorem is equal to integral over boundary v dl. And this is what people call circulation. Let's take double connected area. Then